Hello, I'm Yongjin Cho of Rehabilitation Biomechanics Lab. Today, I'll present the progress of soft exosuit system for ankle assistance. Sohyun Moon and I do the project together. In this presentation, I'll briefly review the goal of our project, which was described at proposal presentation. Then I'll talk about the current state of our key performances, which proposed before. Future work will also be explained. In this project, we plan to implement soft exosuit system for ankle assistance. The platform consists of actuation unit and textile suit. The overall system can be shown figure at the right. Upon this hardware system, we have two tasks to run the system. First, we need to find out the characteristics of gait because those are all different for everyone. So will implement the gait phase detection algorithm. Also, we will do a trajectory planning for the motors which are used for dorsiflexion and plantarflexion assistance. First, I'll explain the gait detection algorithm. To detect the gait phase, we used IMU sensors. After a few minutes of walking trial, data about acceleration and position can be taken by accelerometer and gyrometer. However, because the data also contains Gaussian noise, we use Kalman filters to correct the data. After that, we calculate the rotation angle using the data. The graphs shown at the right are the rotation angle of two people during walking. The positive value of degree is occurred when angle shows plantarflexion motion, and negative value is shown when the ankle is at dorsiflexion motion. Using the data of the state of ankle angle and acceleration of ankle rotation, we can divide the phase of gait cycle. The circle at the graph is colored according to the phase of gait. Through this, we can find out the timing of the situation such as heel strike or toe off. To make motor trajectory for ankle assistance, we need to model the system. Although the force is transmitted through the cable, body and suit are also changed. Therefore, we need to model the system about the body, cable, and the suit. When the force is generated by motor, two forces are applied at the system. One is cable itself, and the other one is from the suit. So we need to consider those together. Also, the system has several sources of compliance. Figure at the right shows those sources. In the bolt and cable, outer shells can compress and inner cable can stretch. Textile material of suit can stretch too. The body itself can stretch because of the tissues between the textile suit and bones. So they have stiffness of K-body, K-cable, and K-suit. The relationship between force and displacement can be represented by K-total, which comes from all three kinds of stiffness. The equation for total stiffness can be shown at the slide. Then we need to determine the force of assistance. Although over 500 Newton of power is needed to lift up the body at the propulsion phase, our maximum force is 250 Newton because of hardware limitation. The maximum force for dorsiflexion is 150 Newton, which is less than plantarflexion force. However, the magnitude is enough because it has to bear not whole body but only ankle. Even though the neurological disorder patients have symptoms of high stiffness when they do dorsiflexion motion, the 150 Newton of maximum force is enough. As we know the desired force and stiffness, the length of displacement can be calculated. Based on the displacement, the rotation angle is also determined. To make a trajectory, we first use the data of gate to determine the timing of assistance. As the gate detection method is not completed, we first use the data of gait cycle of average people. In the case of plantar flexion, the cable starts to apply a tension at the 40% of gait phase. It reaches its maximum assistance force at the 62.5% of gait phase. After that, it returns its original state when the gait cycle is at 83%. The exact theta value can be calculated using the radius of pulley r and the displacement length x. We determined to make the trajectory as trapezoidal one. It consists of three phases. First one is acceleration phase, then the motor rotates at constant velocity. Finally, the motor decelerates until stop. The equation for acceleration and deceleration phase of trapezoidal trajectory is shown at the slide. Now I'll explain the upcoming tasks of our project. We detected the gait cycle and divide the graph of rotation angle as several phases. So we will find out the specific timing of situations such as heel strike, foot flat, and toe off. After we know these timings of gait, we can use this to make more precise motor trajectory for assistance. About the control process, because we made the trajectory only for plantar flexion motion, we need to make a trajectory of dorsiflexion motors. Also, the force value will be used for feedback control using load cell sensors. After that, we will do experiment using apparatus and measure the rotation angle to validate our system. As mentioned before, we cannot do experiment to human because IRB permission is not approved. Therefore, we will run experiment using apparatus which is shown at the slide. The footplate axis of our apparatus can be measured using encoder which is attached to its axis. The torque sensor is also applied, therefore we can measure the torque to rotate the ankle. Through this, we can determine the performance of our soft exosuit system by measuring rotation angle of ankle and the amount of force to assist the rotation. This is the end of the presentation. Thank you for listening.